In this hopefully short video, we will discuss some of the assumptions that we make when fitting linear regression models. Now, it may not be immediately clear what this video has anything to do with the 3 videos that have come before it, but hopefully by the end of the lecture, it's clear how these ideas are all related. When we fit a linear regression model, the underlying assumption is that there is some true linear relationship between our features and our response variable. But we don't actually get to see what this true relationship is. Instead, we see a noisy version of it, and that noise comes from this epsilon term that we also discussed when looking at the bias variance trade-off. I'll revisit this slide in a second, but I want to look at an example in terms of simple linear regression. So over here in the right, I have the graph of some function f theta star of x. And the inputs are, some points on the x-axis, and the outputs you can see fall exactly on this straight line, which seems to be defined by, 2 plus 3x or something like that. So there's some true underlying relationship that involves my x's, and this is what we are trying to determine. But we don't get to observe this straight line. We will never see this in a modeling task. Instead, we will see this bottom right scatter plot, where our x values are unchanged. The y's that we see are the result of taking the outputs of our true linear relationship, so taking the height on this line, and adding or subtracting a little bit, and that's where the random noise comes in. So you can see the points on this scatter plot roughly follow the same straight line as the one on the top right, but some points are slightly above their position on the top graph, and some points are slightly below their position on the top graph. So we are assuming the y's that we observe are the result of some true linear relationship, f theta star, plus some random noise. Now, when we talked about the bias variance decomposition, we said that this random noise term was independent and identically distributed for each observation. This epsilon term is the reason we aren't able to see this true relationship. If you remember in the bias variance decomposition lecture, we saw that this random noise term was independent and identically distributed for each observation. So it follows the same distribution for every one of our observations I, and it is independent for each of our observations, meaning that the vertical spread from the sort of line of best fit should roughly be the same across the entirety of our x-axis. So these are the assumptions that we are making, and let's revisit the more general multiple regression case. So we have our design matrix X, which we actually can see. So for instance, the x-axis on this scatter plot, this is where our training data comes from. We also get to see these y values, but these y values are a result of multiplying our design matrix X and true parameter vector theta star and this random noise term. And in this formulation, epsilon is a vector with n elements in it containing the noises for each of our n observations. The reason these two sort of text boxes are in red is because we don't get to see what theta star is, and we don't get to see what the noise element is. All we get to see are the x's and our y's. Our goal when performing linear regression is to estimate theta star to the best of our ability, because theta star defines the underlying linear relationship between our inputs and our outputs. And this is what we've been doing all along. We called theta hat the optimal model parameter because it minimized mean squared error or regularized mean squared error on our training data. Theta hat, the way we've defined it, is actually an estimate of theta star. This definition here you can think of as being a function. It takes in training data, so it takes in a design matrix X and response vector Y, and it spits out an estimate for what it thinks theta star is based on the sample we collected. But of course, if we had different training data, so if we had different observations in our design matrix X and response vector Y, then our guess for theta star would be different. And so this is indeed an estimator, and it's often referred to as being the least squares estimate or least squares estimator because it is the estimate that minimizes mean squared error on our training data for the model y is equal to x times theta. Now, I really want to stress that what we are doing here is really nothing new. It's just a more statistically rigorous perspective on things we've already seen. we still find our optimal parameter vector or estimate of the true parameter vector the same way, and we still make predictions the same way. Our model is unchanged. To make predictions for what we think predicted y values should be, we take our design matrix X and multiply it by this optimal parameter vector theta hat. The only reason I bring up this set of assumptions is because in the next video we will start trying to interpret what our model's parameters mean. And again, that's sort of the point of inference, using our model to understand relationships between our features and our response variables, as opposed to sort of just trying to predict things accurately.